Hi everyone. For this tutorial we are going to look at curve generation, and we are going to do some connection between two curves to create this sort of net effect. And for this exercise we're going to work with random and some curve division tools and learn some overall properties of how we can filter some geometry based on its length. So we're going to start building this from scratch. So let's see how we can approach the random curve generation. So I'm going to start by creating a list of points, and these are going to be done with a series. And you can stack these in any orientation in the coordinate system. So I'm going to do them along the x-axis. We're going to space them out a bit and supply some numbers for their spacing as well. So after you create something like this, we can actually connect them by using a polyline, right? So we can just type up polyline here, and that will create a straight line connecting these 6 points. But what I want to do today is do NURBS curves, which are non-uniform rational B-splines. So they're going to be interpolated through points in 3 dimensions. So for that one, I'm actually going to change the y and z coordinates of these points. So let's look at how we can do something a bit randomized. So we already have a random function built. So let's look at how random works. And random actually takes in a couple of inputs and outputs a random value. So the R stands for an interval, which is between 0 and 1, and is between n actually is the number of values, and s is the seed value. So the R stands for a domain. You can actually plug in a single number here, which will set up a domain from 0 to that number, but you can also go to the Math tab, and under there's construct domain, and you can actually structure a domain with some intervals. So let's say we want all the values from let's say 3 to -3. So I can set up a custom domain interval like that and feed this in. And let's say we want some numbers, right? Let's say we want 6 numbers within that domain. So that will give me values, random values between -3 and 3. And we can feed in any type of seed value here, which will change how those random values are computed. So I'm going to use this logic behind random to build some curves. And the amount of random values we need has to match the amount of points we create along the x-axis. So what I'm going to do is copy this number count to the random and feed this in to, let's say, the y coordinates of these points. And you can start seeing that those values are actually randomized now. And we can do something similar in the z direction as well. And for z direction, I'm just going to make another copy of the random. You can actually change the seed value here, because otherwise you will generate the same values. And I can set up a height value for the z, so that now the random interval will be set from 0 to 4, as I mentioned, and the output will be between 0 and 4 as well. And we can feed this in for the z values. And these are the points that we're going to be working with for the first curve. So after we created our first set of points, then we can actually connect them in a bunch of ways. So if you go to the curve tab, under primitive, we have under spline, we have NURBS curve, polyline, and interpolate. These are actually different curves. So polyline actually connects these points using straight lines, linear interpolation. So it connects every single point, and it gives you basically a curve with kinks or breaking points. Another way to connect them would be interpolate, which actually connects these points using a curve that actually visits these points, right? So interpolate curve function actually goes through these points as well, but it draws it as a curve. Another way to connect them would be the NURBS curve. A NURBS curve is somewhat different than these curves. A NURBS curve actually takes in these points as CVs or control vertices, and it calculates kind of a mathematical interpolation that is kind of like a quadratic function. And it doesn't go through these points, but it kind of interpolates the data through them. So we're going to we can use a bunch of these for today's exercise, but I'm going to stick with the NURBS one for the first curve. So we're going to do use this curve first. And I want to create a second curve that is maybe interpolating, but I want it to be somehow offset and randomized as well. So for that one, we can actually copy this whole thing here. You can change the number of points you want. Let's say we have a bunch of different points, like 8. If I do 8, then it becomes somewhat longer. Let's keep it actually at the same interval. But I want to move this first outside of this curve. So I want to add some value to its y coordinates. So you can do it by adding some value to the y values, and you can create an offset of this curve. And you can also start randomizing the second curve function as well. So if I change some of these seed values and some of the interval values, the second curve would also change. I can also change how the z interpolation works, right? So I can play around with the seed value for the z generator, and I can choose a curve that I like. And I can also make them adjacent, make them closer to each other or further apart. Let's see. So I'm going to play around with these a bit, and let's say I'm satisfied with this curve here. The next step is to use these two curves. So for this one, let's use interpolate curve. So I'm going to interpolate the second curve, and you can see the difference. So this curve actually goes through those points. The bottom one actually, if I bake the NURBS curve, let's say if I bake this, and then you look at the control points of the second curve, you can see that they coincide with the input points. It's because that's how it's drawn. So it's almost like rebuilding a polyline to a higher degree. In the next step, we're going to hide the control points that we use to model these random curves, and we're going to look at some curve functions. So remember that our intention was to build a net between these two curves. So in order to create a net, I first have to connect these, and for connecting them, I need to divide them into points. So that type of division we can actually control by the division under curve division. You can divide a curve using numbers. You can divide it using lengths or distances. We're going to start with divide curve using equal lengths. So this one, let's say we want to divide it all the way up to 20 points. And this curve division gives us points, tangent vectors, and parameters along that curve, coinciding with the location of these points. And you can see that it starts from the beginning of the curve and ends at the end of the curve, and it spaces out the points uniformly along the curve. I'm going to do a similar number of division for the second curve, so I'm going to copy this one and paste it. And for the second one, we're going to stick with the same number of division, but I'm going to use the second interpolated curve. So now we have the same amount of points on both lines. So the next step is to divide, to connect the divisions. So let's actually, we have already divided them, so let's connect them using lines. Now, if you increase or decrease the point count, you can see that this almost gives you kind of a sectioned view of a surface, right? So this is kind of a like a lofted surface between these two curves, and we are dividing it into points and connecting it with lines. So this is kind of showing us how kind of a net could be formed between these two curves. And in the next step, we can actually do a few things. So for instance, if I divide these points to get some intermediate divisions, we can create kind of a gridded division. but my intention is to actually control maybe the length of division. So you can see that some lines are longer than the others. So what if we want these lines to be equally divided up, right? So let's say that I want to take, and this time do a division, so division by length. So let's say if we divide length, so I grab the curves and specify some length threshold here, which could be anything we want. So let's say 1.5. And you can see that the longer curves actually get more division and the shorter ones actually get less division. And I can lower the threshold and more points could be added. The division starts from the start of each line. So you can see that the A point signifies the start of each curve. So we can see how many division we get here. And let's say that we want to combine these lines to draw our net. So here I have the length parameters. If I want to connect them along the x direction, let's say we want to go through them in the other direction, there is something that we could do here. Let's look at the data that we have first. So we have 42 curves, and we divide each of them by unit 1, and each curve has a different length. So that means each curve will output a different number of points. So some of them give us 3 points, some of them 4, some of them 5. And let's say we want to go through this data and connect them not in the lists that they are located, but horizontally in the other dimension. One way of doing it would be to use flip matrix. So if I do flip matrix, this actually flips the type of data that we have, and it will create 5 lists. It will actually create the maximum amount of points lists, and it will give us kind of a data that we can connect horizontally. Actually, before showing you divide length, maybe to understand this a bit more, I can do it this way. So if you do another division here, let's say divide curve again, divided these up to 5 divisions, which will give you uniform division, but you can see that their spacing is not uniform, right? Because some lines are shorter than others. Now, if we did flip matrix to this, and we get 5 lists with 42 points, then I did a polyline through those, you can see that this data goes kind of parallel to the first 2 curves that we have made, right? So if I hide the initial construction, you can see that we are actually combining the divided points by flipping the matrix. Now, this will happen without any problems if we do divide curve, which will divide it uniformly. But if we use divide length, then some curves will give us less points. Now let's see what happens when we use flip matrix with divide length. So if I combine it here and disable this part, now you can see that some lines are actually not combining properly, right? So here we have some data that goes through the curves. So if I visualize these first 2 curves that we had, here you can see that some data points are actually traversing the lists that they are, where they are located, right? So this point, for instance, here, this point is going straight up to the next point in line. So let's say we want to get rid of this type of interpolation. One way of filtering this would be to actually explode each curve. So I can simply explode these curves here, and you can just after the polyline, you can just flatten this list so that it becomes a single list with single polylines. And now we will have we can actually do it here. I think we can also do it to the segments, so we can treat them all individually. So if I flatten it here, we now have individual line segments. And if you look here, you can see that some lines are longer than others, right? So some of them are like equally spaced, whereas here the data doesn't find any corresponding divided point and it goes through the list. So we can actually get rid of those lines. So one way to get rid of them is to look for their lengths. So we could do curve length. we can look at their length parameter, and you can see that average length is within 0.64, so these lines are longer than 0.64, so we can create some sort of threshold here. Let's call it 0.8, and we can look for if these lengths are smaller than 0.8, right? So this is a logic operator, and what it does is it compares two values under this condition, smaller than. If the comparison is smaller, then the output would be true. If it's not, then the output would be false. And using this type of comparison, and these are actually located under math operators, you can also use larger than some threshold. But using this, we can combine it with a dispatch to filter our data. So under this smaller or equal to sign, you can see that we're getting a true-false comparison. There are 184 line segments here, so some of them are smaller than the threshold, some of them are larger, and we want to find out which ones are smaller. So I can use this data here, use it as my filtering pattern, dispatch pattern, and filter the list of line segments. So combine it here. Now under A and B, we will have different sets of curves. So here, if you look at curves B, you can see that we caught these two curves that are longer than the rest. And what we want to use is the curves that are in the A list, which are smaller than the threshold. This is somehow important because if you change some of these parameters, you may want to create this sort of filtering so that you don't have this sort of irregular data in how you create or build your net between two randomized curves. And one other thing we could also do, if you look here, you can see that the first row of points, they actually coincide with our first curve here. So under NURBS and interpolate curve, these were setting our boundaries for the two profiles. Let's actually pipe those to visualize them a bit better. So let's say we pipe them at 0.1, and I can hold shift and attach the second curve as well. So these are the two piped curves. Now if you go all the way to the end and look here, the first polyline actually coincide with our first curve. So let's say we want to get rid of these first values, first points in the flipped data, or we can also get rid of them under divide length here. You can actually look here and you will see that there are rows of points, right? So these are the points along each curve. So there are 42 curves, and each of them are divided with some length threshold that we defined, and they are giving us different numbers of points. So to filter out the first point of these lists, we go to sets, list, and we do shift list. So we can offset all items in a list using an index. So how do I want to offset the data here? Let's say the shortest curve has 3 data points, right? So these 3 points here, I want to get rid of the first one so that we have 2 points left. So I can combine the data, all of them, at the shift list. I want to offset it by 1, so I want to get rid of the first item, but I want to turn wrapping false, because wrapping actually offsets the data and wraps it to the end of the resulting list. So if you do it false, now if you look at the data, initially we had 3 points, now we have 2, 3, and 4, so 1 less. And visualizing the lists, you can see that the first row of points have been shifted. All I have to do is plug this in to the flip matrix, and that first row of points will be gone because we have filtered them out here. Now we can actually change our threshold. We can add more division here, and we can actually hide these as well, and we can hide the dispatch so that we can see how the resulting point division works. And this is basically building a parametric net that is length based between 2 randomized curves. So you can actually change the first curves as well, make them longer or shorter. So I can maybe reiterate the numbers here make it longer as well. And you can see that our curve is being built. So here I'm getting some, let's see, an error. Probably the length threshold is actually not working. So let's see, the average lengths here are 0.9, so all of them are getting filtered out. So let's say that we want to increase this all the way up to 2. You can actually start looking at how the filtering mechanism works and maybe create custom grids or divisions in your net as well. And in the last step, you can just pipe these curves too. So let's make them 0.05. Let's make them thinner than the boundaries. Let's say 0.03. And I'm going to do the same to these curves as well. So you can just hold Shift, connect it to the pipe, and we have ourselves 2 randomized curves and a net between them calculated by distance. So in this tutorial, we covered some of the basics of creating randomized curves in 3D using the random function. We looked at domains, intervals. We also did look at NURBS curves, interpolate curves, and polylines. We divided our curves to numbers, using numbers, and we divided them into points. We combined these 2 curves with lines. We also looked at divide length. And we looked at how we can actually filter some of the data using shift list, flip matrix, and looking at the length of each segment, line segment, and filtering it out with dispatch. So this is kind of a linear way of filtering the set, but you can also create some parametric variations and see how these tolerances act. And again, you can just play with the shuffled parameters or randomized parameters, or make it longer or shorter, change the interval of the points, and investigate some variations with this net. And this week we looked at basically these sorts of additional curve functions. Next week we're going to look at graph mapper and curve-oriented perpendicular planes, and how we can construct some more complex geometry using curves as spines. And if you have any questions, you can leave comments below, and I'll see you guys next week with another session, and thanks for watching.